Massive automated manufacturing facility? I mean, really looked at it. It's basically a sprawling ecosystem of sensors, valves, and controllers. And honestly, without a rock-solid underlying structure, that ecosystem is just a ticking time bomb of operational chaos. So welcome to this explainer. Today we're going to unpack the absolute genius behind the Somatic PCS7 blueprint. We'll see exactly how it takes these insanely chaotic physical processes and maps them into a totally scalable, perfectly ordered digital architecture. Okay, let's just dive right into it.
Here is our roadmap for today. We've got 5 key pillars to cover. First, the digital twin reality. Second, architecting the plant view. Third, strict blueprint constraints. Fourth, bridging logical and physical. And finally, scaling the digital ecosystem. Starting off with Section 1, the digital twin reality, understanding the 2 lenses. All right, the big picture philosophy behind PCS7 is pretty fascinating. To build a digital twin that actually works, you have to completely separate the physical hardware from the industrial process itself. You can't just mash them up into one big tangled mess, right? Instead, engineers look at the system through 2 completely different lenses. On one side, you have the component view. Think of this as the physical reality. It's where your CPUs and your networks actually live. But on the other side, you have the plant view. This is the logical reality, and it's structured entirely by the technological process, broken down by plant, unit, and function. Now, what's really interesting here is the stark contrast between these 2 worlds. In the physical reality, things are incredibly rigid. Data is tied down to very specific, physical stations. But the plant view? It's fluid. It operates on S88-style factory logic. This is where the actual heartbeat of the process lives. We're talking the tanks, the pipes, the physical flow of materials. The system essentially organizes the whole project technologically, completely ignoring where that hardware might physically be sitting in some dusty server room. When you put these architectures side by side, it's obvious they operate under entirely different rulebooks. The component view cares about station topology, while the plant view is all about the process sequence. But here's where it gets critical. Check out the S7 program rule. Even though these 2 worlds are separate, they absolutely have to communicate eventually. And let me tell you, the system is completely unforgiving here. S7 program folders across these stations must have totally unique names. And get this, absolutely no spaces are allowed. None. Why? Because those folder names literally define your WinCC connections. Just one stray space, and boom, your operator station loses its connection to the physical hardware. You've suddenly got a catastrophic blind spot right on the factory floor. No pressure, right? Moving right along to Section 2, architecting the plant view, building the nested logic. So, knowing that the plant view represents our logical process, how do we actually construct it so it's, useful to a human operator? Well, this is where the automation architect steps in. When an engineer sits down to build this, they aren't just sketching pretty pictures. They have to nail 3 specific objectives. 1, translate the physical process into a multi-project environment. 2, define incredibly strict hierarchy levels. And 3, build a vital, unbreakable bridge between those abstract digital folders and the concrete S7 user programs that are actually running the machines. To keep this all from spiraling out of control, the engineer maps everything down 4 fundamental hierarchy levels. It's like a funnel. Step 1 is the big picture, the overall plant. Step 2 zeroes in on a specific unit. Step 3 narrows it down even further to an equipment module. And finally, Step 4 hits the exact function, something super specific like heating or mixing. You can kind of think of these levels like Russian nesting dolls, boxes neatly packed inside of other boxes. This is called the encapsulation rule. Lower hierarchy levels are strictly encapsulated by the higher ones. You can't just drag and drop a folder wherever you feel like it. They are rigidly named and contained based purely on what they actually do within the technological process. Let's actually ground this in reality for a second and look at the Johnson plant. We start right at the top at level 1, the Johnson plant itself. Then we step down into level 2, the reactors unit. Inside those reactors, we find level 3, which is equipment module R310. And right at the bottom, level 4, we hit the highly specific dosing function. Because of this, every single process tag and piece of code is locked inside this unbreakable structure. As an engineer, you literally never have to guess where a piece of code belongs. It's brilliant.
All right, Section 3, strict blueprint constraints, the law of the land.
Now, I know it's super easy to look at syntax rules as, well, boring limitations. But in a massive automated factory, these rules are absolute laws. They are the only thing keeping your digital twin from totally collapsing. Take this number, for example, 255. Lock that number in your brain because it is a hard, unyielding limit that can literally make or break your entire project architecture.
So, what is 255? It's the absolute maximum character limit across all of your nested hierarchy levels combined. Because you only have 255 characters to work with, engineers have to be incredibly strategic. They abbreviate folder names at the top levels just so they don't run out of space when they get down to the tiny equipment details. And it gets stricter. Certain characters, periods, percentages, slashes, even spaces are completely banned. The system acts like a ruthless bouncer. It aggressively sanitizes any of those invalid characters, instantly swapping them out for a $sign the moment you try to compile. And it's not just doing this to drive you crazy. It does this to guarantee a perfectly clean syntax for the HID, the higher level designation. The HID is basically a critical origin message that tells an operator exactly where an alarm is coming from. If that syntax gets messy, the alarm is completely useless, and you've got a huge problem on your hands.
These constraints are baked right into the configuration matrix too. The system lets you have a maximum of 8 nested levels, and each one of those is hard capped at 24 characters. But here's the really cool part. If you enable the Derive Picture Hierarchy option, the system uses those strict rules to automatically generate the visualization layout for the operator station screens. That means the invisible backend structure you just built literally draws the navigation menus that the factory workers are going to use on their monitors. It's all connected.
Okay, here is a wild checkpoint insight about how much control the system actually takes. Let's say you build out your folders in chronological order. Maybe you make folder D first, then Z, then A. Well, the system does not care about your timeline. It entirely ignores your human chronological entry and aggressively forces an alphabetical autosort right through a funnel. It relies exclusively on those precise naming conventions to standardize the twin. This ensures that whether you're the lead architect or a junior dev, every single engineer looking at the project sees the exact same logical flow. Moving to Section 4, Bridging Logical and Physical, Connecting the Two Lenses.
So, we've got our perfect logical blueprint, and we've got our physical hardware. How do we actually bridge them together? It all comes down to the AS/OS assignment. AS is your automation system. Think of that as the controller. OS is the operator station. That's the screen. To link them, we use the inheritance rule. Let's say you connect a top-level logical folder, like Johnson reactors, to a specific CPU and a specific WinCC application. The second you do that, magic. Instantly, all the lower-level nested objects inside that reactor folder automatically inherit that exact same hardware assignment. You build the bridge once at the very top, and that logic just cascades down to every single valve, pump, and sensor underneath it.
And finally, Section 5, Scaling the Digital Ecosystem, the Parallel Payoff.
You might be asking yourself, why? Why go through all this meticulous, obsessive-compulsive organization? Well, it's all for the operational magic trick of scaling. In a real-world multi-project environment, you don't just have one lonely person working on a factory. You might have dozens of engineers spread out everywhere. The synchronization rule is what makes teamwork possible here. You set up a master source hub. If you modify the plant hierarchy in that master project and hit Update, the system instantly pushes those structural changes outward to all the linked user projects simultaneously. Just like that, everybody is kept on the exact same page totally automatically. And this brilliantly illustrates the ultimate superpower of this whole system, parallel processing. Because the nested hierarchy is universally standardized, you can basically slice the project straight down the middle. Your automation system engineers get their side of the project, they dive into the charts, the logic, the code, but they don't touch any pictures. At the exact same time, your operator station designers get their side. They build out the graphical screens, the buttons, the UI layouts, but they don't mess with any code charts.
Which brings us to the ultimate takeaway. By linking the plant hierarchy across different user projects, automation engineers and UI designers can work in parallel on the exact same structural blueprint without file collisions. Think about that. All of this military-grade organization, every single one of those 255 character limits, and all those banned symbols, they all exist for one reason, so that massive teams of humans can build out a gigantic factory ecosystem at the exact same time without ever stepping on each other's toes.
Which leaves us with one final thought to chew on. When you look at how your own organization handles its complex data and massive projects, you really have to ask yourself, does your digital architecture enforce true order the way the PS7 blueprint does, or is it merely documenting the chaos? As we've seen today, strict constraints aren't actually there to hold you back. They are the secret key to unlocking limitless engineering scale.
Thanks so much for